In some of our previous examples, we saw that water can act as an acid. In some of the other examples, we had water can act as a base. Water can actually react with itself and do an acid-base reaction, forming hydronium ions and hydroxide ions. We call this the self-ionization of water. In the self-ionization of water, water as our acid would donate the proton to our base, our proton acceptor. When that occurs, we end up with our acid here, the conjugate acid of our base. You can see in red, the water has accepted the hydrogen ion from our water as the acid. And then what's left behind when this is gone, we have our hydroxide ion, which is our conjugate base for the original water acid. So this reaction actually occurs. You can notice in the arrows here that the arrow to the right is smaller than the one to the left. This should be really, really tiny arrow. Primarily, water stays together as molecules, as what's shown in this beaker down below. There's a very few amount of ions that are produced. It's about 1 per every 500 trillion molecules do we have ions. So this picture here is not really representative. It's showing here's our hydroxide ions in purple, and in blue we have the hydrogen ions. It's such a small amount that if you were doing your light bulb experiment and you were seeing if water would conduct electricity, your answer would be no, because there's no ions. So it's such a small amount, we would never be able to detect that in the light bulb experiment, and it's really considered negligible. But it's these amount of ions that we're producing we're going to be using in future calculations. We can measure the amount of ions that are formed in the self-ionization of water. This is what we call a constant Kw. The ion product of water, how much we formed. The formula for that is Kw is equal to the concentration of hydronium ions times the concentration of hydroxide ions in molarity. So the brackets here means the concentration of the ions in molarity. If we were to determine what that number is, we would find out that Kw is equal to 1 times 10 to the negative 14th. That's how many ions we have. This Kw number we're going to be using in some calculations. This number will be given to you. I do want you to know the formula for Kw when we do some future calculations. So again, this is a very, very small amount. So 1 times 10 to the negative 14th would be, you have all these zeros in front of it. It's telling you it's a very, very tiny number, however many that would be until you got to 14th. That's probably not even enough zeros. That's, again, a very small amount of ions. This is, again, the concentration of hydronium times the concentration of hydroxide gives me this tiny little number here. In pure water, the concentrations of hydronium ion and hydroxide are equal to each other. So again, we're using our formula here. We have 1 times 10 to the negative 14th came from the formula where Kw is equal to hydronium times the concentration of hydroxide ions. So Kw was plugged into here. It's 1 times 10 to the negative 14th. We could actually solve for the concentration of the individual hydronium ions and the concentration of hydroxide ions by doing an algebraic problem. So if we wanted to say my concentrations are equal to each other, we could call both hydronium x and hydroxide x. And x times x gives me x squared. To solve for x, I would take the square root of both sides, and the square root of x squared gives me x. The square root of 1 times 10 to the negative 14th is 1 times 10 to the negative 7th. So again, what this is telling me, this is the concentration in molarity of x. X is hydronium ions and hydroxide ions. This is occurring at about room temperature, about 25 degrees. So if we have a neutral solution, the concentration of hydronium ions in our solution is 1 times 10 to the negative 7th. Molarity, or moles per liter. The concentration of hydroxide ions is 1 times 10 to the negative 7th moles per liter for neutral solutions. This slide graphically illustrates that the concentration of hydronium ions and hydroxide ions are equal to each other. And we just figured out in our previous example that the quantities, if we were measuring the molarity, is 1 times 10 to the negative 7th molarity for both of those because they have equal concentrations. Now, if you're given the concentration of hydronium ions and you're asked to calculate the concentration of hydroxide ions, we can do that using our formula Kw is equal to hydronium times hydroxide ion concentrations. And again, the Kw constant value would be given to you. So then we're basically just going to use our formula and we'll plug in here. So Kw is 1 times 10 to the negative 14th. And that is equal to the concentration of my hydronium ions, and again this is all in molarity, 1 times 10 to the negative 3rd, and we're solving for hydroxide ion concentration. That's our unknown, so we're leaving that as hydroxide ions. In order to get the hydroxide ions by themselves, we're going to divide both sides times 1 times 10 to the negative 3rd, and we're doing this in order so we can cancel our units on the right of the equation, and then we end up with hydroxide ion concentration by itself. So you could plug these numbers into your calculator, 10 to the negative 14th divided by 10 to the negative 3rd, and you would get an answer. In chapter 1, I talked about multiplying and dividing exponents and adding and subtracting exponents, and I said you're welcome to use your calculator, but just as a review, a shortcut way you could do that, if you have exponents, you can actually subtract them when you're doing division. So we would have negative 14. When we do divide by with exponents, you're actually subtracting it. So that's minus a negative 3. And then we could just say negative 14 plus 3 is going to give me negative 11. So for my answer, it's 1.0, because 1 divided by 1 is 1, times 10 to the negative 11th. So again, you're welcome to use your calculator, but that's sort of a shortcut way you could do it that might save you a little bit of time. So what this is telling us, this is the concentration of hydroxide ions. We know our concentration of hydronium ions. So the reason we're learning how to do this is to tell us if our solution is acidic or if it's basic. So I want you to think about what makes an acid. An acid is something you put it into water and you form hydronium ions. So with water self-ionization, we're basically determining, do we have more hydronium ions or more hydroxide ions? And based on that, we could tell if our solution is an acid or a base. So in this example, we have hydronium is 1 times 10 to the negative 3rd. Hydroxide is 1 times 10 to the negative 11th. So whichever number is larger is going to tell us if it's an acid or a base. So 1 times 10 to the negative 3rd is a much larger number. Remember, these are exponents, so the bigger the negative exponent, the smaller the number. So 1 times 10 to the negative 3rd is 0.001 versus this one, you have a bunch of zeros. I should count these correctly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this obviously is a much tinier number than the one up here. So it means we have more hydronium ions, so our solution should be acidic. And that's why we're doing these calculations, is to determine if our solutions are acid or base. If the hydroxide ion concentration is 1 times 10 to the negative 2 molarity, what is the hydronium ion concentration? So again, we're going to use our formula. Kw is equal to hydronium times hydroxide ion concentration. And then we're just going to plug in. Again, you need to know the formula. I will give you the Kw, your constant. 1 times 10 to the negative 14th is equal to, we're looking for hydronium ion in this example, and we're going to plug in our hydroxide ion concentration of 1 times 10 to the negative 2. So again, we divide both sides by 1 times 10 to the negative 2. So we can isolate hydronium ion by itself to get the concentration of how many hydronium ions are in our solution. So we have, in this case, we can do our subtraction. Negative 14th minus a negative 2 gives me negative 12. So my hydronium ion concentration is 1 times 10 to the negative 12. And then again, I may ask you a question. Is this solution an acid or a base? And it's based on, do I have more hydronium ions? Because that's what an acid is. It produces hydronium ions. A base you put in water and you get hydroxide ions. So more hydroxide, base, more hydronium, acid. So in this example, we have 1 times 10 to the negative 2 hydroxide ions is much larger than 1 times 10 to the negative 12 hydronium ions. So this solution would be basic. The quantity of hydronium ions compared to hydroxide ions is how we can determine if we have an acid or a base. If the quantities happen to be equal to each other, we're going to have a neutral solution. So solutions with the hydronium ion concentration greater than 1 times 10 to the negative 7th molarity are acidic, meaning that the concentration of hydronium ions is greater than hydroxide ions. Solutions where your hydroxide ion concentration is greater than 1 times 10 to the negative 7th are basic solutions, meaning I have more hydroxide ions than I have hydronium ions. We end up with a basic solution. When my concentrations of hydroxide are equal to hydronium, then we have a neutral solution. So graphically, we can also look at our hydronium hydroxide ion concentration. So we have the concentration over here in molarity, moles per liter, and then we have a comparison of our hydronium and hydroxide ion concentrations. So if we look at the first one on the left, we have more hydronium ions than hydroxide ions, that we have a greater amount of those, we're going to have an acidic solution. When hydronium is equal to hydroxide, we get neutral. And again, more hydroxide ions mean we have a basic solution.